recording here. We stopped on the bond energies. When I say the bond energy is energy needed to break the molecules into its original atoms. If you have HCl, you break it in H atom, hydrogen atom, and chlorine atom. If you have a fluorine gas, F2, F by itself atom, fluorine atom by itself, the other one by itself. So this is the bond energy. So how we calculate this? We calculate it opposite to the enthalpy formation. The enthalpy of formation, we get the products minus the reactants. So here, when it comes to this one has to be, you don't have to memorize those values. Don't have to memorize these values. Don't have to memorize these values because this has to be given to you. But you have to, for the sake of the final exam, I did not see them in the final exam, but at least you know the formation, enthalpy of formation, they come every year. So they come every year. And if you look at the review files there, they are there every year. So every year they come. This one is very rare, but at least you can put it aside and you know it's the opposite. We have the enthalpy of formation, the products comes first minus the reactant, but the bonding energy will be the reactants minus the products. Why? Because you are breaking in. You are breaking atoms. That's an endothermic. Did you see any of those is positive? No. All the energies are negative? No. All the energies are positive. Why? Because you have to put enough energy to break in. When you form bonds, energy will be given away. That's exothermic. But when you break, you have to put some extra energy to break, help you break the atom, the bonding, correct? So now we have this. The question is, what is the enthalpy change for the reaction, for this reaction? So we have to look at the hydrogen plus fluorine, both of them gas, to give us 2 molecules of, or 2 moles of HF gas. So I'll give you all the information you need. HF, that's first hydrogen, you break it in the middle. For each one, it's 1 bond, correct? Hydrogen has 1 bond, and the 1 bond is this much of energy here. Fluorine, 1 bond, those are 1 bond. You break it in, correct? So this amount here, those values are given to you. You don't have to memorize them. So this is the reactant, by the way. So those are reactants. All those are reactants, correct? So those are reactants. This one is your product. This one is your product. And how many of this is 2? Why is 2? Because here you have 2 moles, correct? So this is the 2 here, and you have to multiply this amount for 1 single bond of HF multiplied by 2. And then you make this one here. This is the reactants. Add them up, minus twice of the product, because you have a 2 here. And this is now, is this. Now, what's unique about this, you can see. What's very unique about this? Come on, you can tell me. I just mentioned it for you guys. When you break in, that's an endothermic. So everything is positive. So here is, look, here is positive. Here is positive. Here is positive. All those are positive, correct? But now we are forming what? HF. So the reaction itself is what? You are breaking hydrogen by itself, gas molecule, breaking the fluorine gas molecule. But when you bring them together to produce HF, the reaction is exothermic. When you form a bond, This is exo. And all those are, you are breaking in, this is endo. So this is very important to know the processes. Breaking a bond, you need energy, that's endo. So positive values. Now, when you're producing a new bond, new molecule, so you can expect the value will have to be negative. It has to be negative because you are forming. So that's an exothermic reaction. So, and everything is recorded. So just follow the whole thing. Now, this is the most favorite one of the ACS exam and the most confusing for the students. Not really difficult. You have just to concentrate yourself on what VSEPR means. VSEPR came out from the abbreviation V for valence, S shell, E is electron, and P is pair, and R repulsion. So what this means here, this method here called VSEPR method, meaning this method here is used to determine the molecule of a shape, the shape of the molecule based on the least repulsion among the bonds among the valence electrons. Let me repeat. VSEPR method is a method by which the shape of the molecule is determined based on the least repulsion among the valence electrons within the molecule. Why we have studied this? This is very good topic in designing drugs in pharmacy, especially if you are fighting tumors, fighting any very complex viruses or something. So you have to design medicine that's really will encapsule this virus and keep it in, or will encapsule the tumor. So this is a wide range of studies for those chemicals, for this medicine or drugs. So we studied this to determine the shape of the molecule itself. So always about repulsion to be minimized. And always we are looking at the central atom for the molecular shape. So for the molecular geometry here, central atom at the middle, correct? So central atom. The key of this here is we have to know Lewis structure. So without Lewis structure, we will not have any clue what's going on. So we have to know Lewis first. Lewis and Lewis dot structure. Lewis dot structure. So if we know the Lewis dot structure, then from there we can look at the central atom, at the edge atoms called terminals, correct? So, and then we can have a table. So this table here will not come. You are not allowed to use it in the final exam. However, for the sake of the exam here and the quiz, you can use it. You can print it out. So you need to print this one out because that will help you to determine the shape, correct? So what it says here, if you look at this, in this VSEPR here, we treat double bond. We treat double bond, triple bond, lone pair, okay, and single bond. So 4 of them. All those are treated as one group. one group. Whether they are double, triple, single, or a lone pair, those are one group. Correct? One group of one group. So we treat them as one group. They are identical. Although they have differences among themselves, but we in this whisper model, we treat them the same thing. So, for example, here I have E is my central atom. E is my central atom. So this is central atom, correct? That's the core of the whisper, the core of the molecule itself. And X is my terminal. X my terminal. So terminal. So terminal means, oops. So E, central atom, CEN. And X is your terminal. Okay, so now if I have something looking like this, central atom and it's connected with both sides, see here, X, just the line here, it's two bonds surrounding, correct? Such as here, for example, C double bond O2, correct? So you'll say to yourself, you make yourself a table here, the code. What's the code? The code is your E here, correct? This is your E, correct? This is your X, and this is X. I want you to write a code in somewhere when you print this one out. This one will be, what will be? E, correct? X2, two terminals. So this is very important. If you have a code with EX2, that is on the side somewhere, this is a whisper code. When I have EX2, there is no lone pair here. Number of lone pair, there is none. So let me take this one out and write it again. So the code is E X. How many X? How many terminals we have? How many edges? Atoms, 2. So no lone pair, no lone pair, correct? So no lone pair. So if I have this the case, the shape of this molecule will be linear, so flat. They are what? They are flat. The shape of the molecule is flat. If I have 3 of them here connected, so this is linear. If I have 3 of them, and the angle here is 180, the linear means 180. And if there are, look at this, look at this very carefully here, guys. If I have 3 of them connected to the central atom, correct? So therefore will be, what's the code here we have for this? I have how many regions I have? 3. Why is 3? You can tell that you have what? You have 2 by just looking at the terminals. The terminals will give you a number of the groups or number of the zone or units. So this one will be, somebody will give me the code of this one here. The code will be, guys, EX3. Yes, that's correct. So the EX3. And this will be trigonal planar, and the angle between the central atom and the 2 terminals is 120. So now that's three zone, correct? 3 zone, because that's 3 here, correct? That's 3. So 3 zone or 3 units, 3 electron pair group. They're called group, units, zone, all is the same thing. So now, if I look at the second one, we have 3 because still E, correct? X, 2, but I have, instead of the third one, I have what? A lone pair. So L, I'll say lone pair is L. L1, one lone pair. So if I add those up, still what? The groups or the units are 3. Still what? 3. 2 plus 1 is 3. However, because it has a lone pair, so that will be bent. The shape of this is called bent or angular. Bent. So the molecule is not. So the flat is here. Bent looks like this. Bent. Correct? Let's take the fourth one. Take this one out. Okay, let's take the fourth one here. I have 4 regions. Let's count them. 1, 2, 3, 4. So this is the code of this will be E X 4. No lone pair, correct? EX4 without lone pair, it is the shape of it, the molecular shape is tetrahedral. What? Tetrahedral. Now, if I start introducing lone pair, so I'll have 3 of them here. I'll replace one of the terminals with one lone pair, 3 of them here, and one lone pair here, guys. So I have E X. When you print it, find the spot somewhere, EX3, and then one lone pair, L1. So if you add those up here, still 4, correct? That's still correct. That's the whole thing is 4. When you look at this, EX3, L1, there's still 4 zone, but you have one lone pair. This is trigonal pyramidal. Trigonal pyramidal. It has. So how you memorize this? You memorize by the code. You look at the code and you can determine. EX3L1. This is a trigonal pyramidal. Now, if you have the same thing here, 1, 2, but you have 2 lone pairs. So the code of this one here will be EX2, correct? 2 terminal atoms. L what? 2 lone pairs. 2 sets of lone pairs. So this one will be bent. One set of lone pair is trigonal pyramidal. The other one is called bent. And you have still 4 zones because you can add those 2. You have 4 zones. Those are 4 zones? 2 single bonds and 2 lone pairs. Here in the trigonal pyramid, you have 3 single bonds and 1 lone pair. And in tetrahedral, you have only 4 single bonds. Correct? You treat the single bonds and the double bonds and lone pair the same thing. So let's take now number 5. Number 5 will get more complicated, but it's not really difficult. As I said, you cannot memorize all of this here, but at least you know up to the 4 here. Up to the 4, I think. Concentrate yourself for the final exam up to the 4. That's what they bring because it's easy to keep track on. When you come into this is a little bit more time consuming because you have to memorize all those, but it's not really difficult here. So if you have a trigonal pyramid, you can have what? You can have bipyramid from the top and the bottom, correct? So you can have bipyramid as well. And the base of the 2 pyramids, one at the bottom, one at the top, is triangle. So how does it look like? You have 5, correct? 5 regions. So the 5 regions are 1, 2, 3, 4, and 5. So you have 5 single bonds or 5 regions. So this code here for trigonal pyramid is E X5. Right, guys? EX5. Now, if you start introducing yourself a lone pair here, so we did here lone pair, correct? So this is called sawhorse. Sawhorse or seesaw. So seesaw or sawhorse. I don't know, but this one looks like there is like a horse, animal horse, and there is in the fish looks like a horse, the head like a horse, and it's acting like this way. So as you can imagine, this is the non-bonding, and this so it looks like a seahorse uh, 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 fish. So but still 5 region. Why? You have E. You replace one of the region, one the single bond. You have 5 in the bipyramid. So here we have only 4. X4, and then L1. L1 means one lone pair set. So this is a seesaw. Now if you replace it with the 2, here is 1, and here is 1. So I'm replacing this one with 2. So this one will be X3 and L2. And remember, this has to add itself to 5. This one has to add itself to 5. And this one is already 5. Here it is. 5. So this called T shape. And if you look with the 5th region here, you have two angles, not one. One with the axis, the axis, and then the z-axis with the x-axis, and then z-axis with the y-axis towards yourself. So you have 2 angles. If you look like the bipyramids, you have the z and x-axis 90 degrees, and then you have 120 degrees with the y sticking out the molecule, correct? And the seesaw, it's like a fish horse. It has 2 angles, the same thing, 90 and 120. This one here, the T shape, it has all over 90 degrees. It has only one angle, 90 degrees, correct? As I said, I did not see them that many times they are inside the ACS exam, but the ACS exam is concentrating about this 2, 3, 4, because those of the chemicals we use in the lab heavily. But some compounds, they have 5 or 6 or 7. So it's getting too complex. Now, if you replace 3 of those terminals with 3 lone pairs, then guess what here? This one here. This one will be, here it is, EX2 L3. So still, you add them up, 5. And the angle is not shown here, but is between 100 degrees, 180 degrees. This is 180. Linear, correct? This is linear. Now you ask me about the angle here in between the y-axis. Out 180. The whole molecule is 180 linear. However, if you come to the other side, it's not 180. All of them itself from the axis here is 180, so linear. If you have 6 without lone pair here, correct, will be your E, X what? X6. That's octahedral. Octahedral is 2 tetrahedrons. You see the diamond. Usually one piece of the diamond is tetrahedral. If you have 2 of those diamonds together based with the, having the same base, that will be octahedral. So in the top, so if you look like this, so this is first, and then this is the second one. So do you have two tetrahedrons? They're having the same base, and that's what's octahedral. Octahedral is double the tetrahedral. Tetrahedral means 4, octa means 8. Octa means 8, and tetra means 4. So two of them here connected. If you look at this here shape is octahedral, twice the octahedral. They say they share the same base, but they are two tetrahedrals together. Now you start replacing your lone pair. Here is 1, correct? And it has to be 6 all the time. And this is five terminals, 5 sigma bonds, 5 single bonds, and 1 lone pair, 6. And the shape of it, square pyramid. Square pyramid. You have less than 90 degrees. Then you have square pyramid, square planar. If you replaced this is 1. If you replace with 2 lone pairs, you have EX4 L2, the square planar. If you replace with 3 lone pairs, so you have 3 sigma bonds and 3 lone pairs. That will be T shape. So this and this is the same, like the T shape of the 5 zone. Here you have 6 zone, here's 5 zone, T shape. And here is the same, linear. If you replaced all the 4 lone pairs with the whole thing. So let's look at the examples here. Let me take this one here out and look at this. Here you have the carbon dioxide. The carbon dioxide, again, want to go and look at the whole thing here, has the same thing. Here is your E. This is your E. Central atom is the core of the molecule. No lone pair. This is X. And this is X. So this is EX2. This is the whisper code, correct? So I come here, say, what is ask yourself, EX2. So I come here, say, where is my EX2? EX2 here, the first one, 2 zones. I have 2 zones, so that the shape has to be linear. So the shape has to be what? Linear. So this is the shape of this is linear, correct? Shape of linear, and the angle is 180 degrees between oxygen, carbon, oxygen. Let's look at this. This one was linear. This one is same thing. I have here, this is my E. This is X. This is X. This is X. No lone pair on the central atom. So it will be X, E, X3. EX3, I go here. EX3, where is it? It's this one here. So therefore, it is trigonal planar. So there's no lone pair, trigonal planar. So this one here will be my trigonal planar, EX3. So you have to find yourself, when you bring this one out, write the codes. Write the codes for each one. So let's go for the second one, for the third one. It is, guys. Now I put for you some worksheets for this. So this is tetrahedral. Why? Again, we have to look at the code. This is my E. This is my X. This is another X. This is my X. This is my X. No lone pair. So this is E X4. So I go to the table here. Where is the X4? So go up, EX4 here, go up. Here, 4 regions, correct? No lone pair. So the answer is here. And no lone pair, that's tetrahedral, correct? So you have to know those codes, otherwise not be able to determine the molecule. Is this coming? It comes all the time. It comes all the time. Those type of questions are always, even if you go for 12-12. Believe it or not, they ask those questions from 12-11. They ask you again. They have to know that you understand this material very well. So now we have here, look at this. We have a molecule like this, OHH. So this is hydrogen combined itself with one oxygen, 2 hydrogens here. So here is one lone pair. Oxygen has to be 8 octet rule. That's 2, 2, and 1 hydrogen. Correct. So how many lone pairs? 1 and 2. Correct. How many regions we have? 2 sets of lone pair and then single bond, 2 of them. So we have E, X, 2 terminals, hydrogen, 2 hydrogens, X2. How many lone pairs? L, we have 2 sets. So I come here, I look at EX2L2. So I come up. Back to the table. So we have to have it handy for. Which one has EX2L2? So just by inspection, I can tell that's this one here, correct? Correct? I have X2. I have 2 sets of lone pair. So the shape will be what? The shape will be this one here. The shape is bent or angular. The shape is bent. So I come here. The shape is bent. So I come here, go all the way down. The shape of this is bent. Let's go for this. As I said, all the way until the 4th. The 5th and the 6th, they are very complex. They don't really bring them in the ACS exam, but they bring you from the first group, 2 zones or 2 units or 2 groups to the 4 zones or groups. So let's look at this. This one here, oops, sorry. This one looks like this. It has one single bond and 3 single bonds. 1, 2, 3. How many zones we have? 4. 3 single bonds and 1 lone pair. 4 bonds. So this one here, I can recognize this one here. The code, with the code E is the central atom, nitrogen. So E, and how many X? How many terminals atoms? I have 3 hydrogens. 3 hydrogens. And how many lone pair? Is 1. EX3L1. Well, so that will be trigonal pyramid, but I have to verify it in going back all the way my table. I have EX3, correct? That's 4 regions. EX3, E1. So this one here, just inspecting this will be my answer. This here will be my answer with EX3 and 1 lone pair. So this is trigonal pyramid. This is trigonal pyramid, correct? So Go further. Let's go for trigonal bipyramid. Trigonal bipyramid. So trigonal bipyramid, it has how many? We said 5. It has how many? It has 5. So, but from this then, if you look at this one here, you look at this. So here it is. This is as AX5, correct? So, for example, it is BCl5. Somebody will name for me this compound. What's the compound name? Phosphorus pentachloride. This one, because the C is not our vowel, so I say penta with pronunciation of the A, because the C is not a vowel. So pentachloride. So this one here has the shape of trigonal bipyramid. So if you look at this, phosphorus will be here, and then chlorine will be here, chlorine will be here, and chlorine will be here. All this chlorine, by the way. So Cl, 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 and Cl. So phosphorus pentachloride is trigonal bipyramid. Well, how I know that? So well, I said this is B is my E, correct? And how many? I have 5 single bonds, 5 regions, 5 groups, 5 units. So 5 single bonds, 5 regions, 5 units, 5 groups, identical. Those synonyms. All of those are synonyms. Groups, units, zones, all the synonyms. So it will be E and the X. How many terminals we have? We have 5. You have lone pair? No, we don't have a lone pair. So EX5, I come here to my table EX5. So I go here, back to my table all the time. So therefore I have it handy here with me. It is 5 regions, correct? 5 regions. No lone pair, which is here. So trigonal bipyramid. Trigonal bipyramid. Now, if I start introducing to this molecule or other molecule the lone pair, then I will have what? I will have a different shape. So here it is. I've introduced to myself 1 lone pair set, 2 lone pair sets. So I replaced the chloride. So 2 chlorides are out. So that will be T shape. One chlorine out, seesaw or horse seesaw, correct? And here 3 of them, I replaced all the chlorine from the plane. That will be linear. So that's, you have first started with trigonal bipyramid, no lone pair. So no lone pair. And then you will introduce those lone pair one at a time, and you can see the difference here. So you can see the name on the shape will be different. So the shape will be different. Now the last thing here is octahedral. The octahedral here, take this one out. The octahedral, you have two tetrahedrals. They are sharing the same plane, the same base. Two tetrahedrals means they make 1 octahedral. A6, that's your see here, that's the code here, whisper code E. There's no lone pair here. No lone pair. L means lone pair. There's no lone pair. So, but you have some exception. You can replace it. You can replace two of the lone pairs here, correct? You can replace one lone pair. So if you replace two of them, you get square planar. If you just only one, you get square pyramid. If you replace three, then you have linear. So if you replace, like you have, this is the central atom, one here, one here, and then you have, this one is replaced by lone pair. This one is by lone pair. This one is by lone pair. And then the rest is, for example, if you replace it here, so the rest is just whatever you have the X here. So that's your X here. That's your X. So we have 1, 2, 3, 4, 5, and here is X here. So if you have three, that will be linear. If you have three, replace three of those, that will be linear. So you can go and verify this here. You have to have the, as I said, print out in front of you. It is, we replaced all of them, four, not three, four of them out, except two, that will be linear. If you replace three, that will be T-shape, correct? If you replace just two, square planar, you replace one, the square pyramid. As I said, six, you can't expect to come, but at least up to the four. So make yourself here a note. Those are mostly heavily covered. Those up to the four zone, heavily covered in the, through the past. That's what I'm. Okay, guys. Now, what's unique about the, so where are we at? Octahedral. Yes, we are finishing the chapter here. So the unique thing about this, all of this one here, of this shape, not only we know the molecule is the shape of the molecule, we can determine its usefulness inside the pharmacy area, but we can look at the whole thing here, and then we can determine the polarity. We can determine what? The polarity of a molecule. Anytime I have, write it down. Anytime I have lone pairs, correct? Anytime I have a lone pairs here, all those lone pairs here, here I'll circle all those lone pairs here. Here, lone pairs, lone pair, lone pair, lone pairs, none or non-bonding, lone pair here, here, here. What effect they have? They have tremendous effect. This is one here, and those here, and here. If you have a lone pair on a molecule, the molecule has to be polar. Blindly, you don't have to look anywhere. The molecule has to be polar. Why? Because those lone pairs are forcing the molecules to spread out and be polar, correct? So polarity means they can conduct electricity, they can dissolve themselves in H2O or polar solvent. So there's a lot of information you can get. Anytime I don't have a lone pair and I have a symmetrical molecule, they are the same, XXX, all those the same atom. This is polar, non-polar. This is non-polar. This is non-polar. But if I have a difference atom in between, that will be polar. Let me show you here some example here. Here it is. Let's look at this. Correct? What do you think about this? Is it polar or non-polar? It is non-polar. Why? Because you have, this is symmetrical. You have hydrogen atom all over the place. Correct? This is non-polar. To make it polar, I have to replace one of the hydrogen at least, but another atom, chlorine. That will be polar then. The molecule has carries out, the molecule carries out the same atoms, that will be, we call this molecule symmetrical, and it's not polar. If the molecule carries out at the central atom, not at the terminal, lone pair by themselves, molecule blindly has to be polar. Has to be what? Polar. So now you tell me. So here it is. Here we did. Look at this. We made out of non-polar a polar. So this is not symmetrical because you don't have the same atom all over the place. So now let's look at this. Is this polar or non-polar? It said in the top polar. Why is polar? Because you have what? Two different atoms. If I replace this one here, I say replace it with another chlorine. For example, I put it here instead chlorine. So, and then put whatever the valence electrons. So what do you think? Is it polar? No, because chlorine, the same atoms. That's not polar. If I replace this one here with hydrogen, hydrogen, let me take this one here out. So if I have here hydrogen and hydrogen, this is non-polar because you have the same atom. If you have the same atom, polarity is 0. But if you change the atoms, then polarity is present, correct? There will be unequal sharing of electrons, correct? So let me go another example here. Is this polar? Is this molecule polar? Yes, no? No, it's not because the same atom, correct? The same sharing, equal sharing of electrons, valence electrons. Same atom, not polar. So how about this one here? It is polar or non-polar? What do you think? Come on, guys, don't let me down. It is polar. Why? This is hydrogen here, but this one here is totally different. This is chlorine. So they are not equal. So that not symmetrical, not equal atoms. So this is polar. But if you have something looking like this, what do you think? This is non-polar. Why? Because you have hydrogen, hydrogen, hydrogen. This is non-polar. How about H2O? You tell me the same hydrogen here, you'll think that is polar, non-polar. But what we have said about the lone pair, what we said about the lone pair? So we have two sets of lone pairs. So it has to be what? Polar. Now, before we finish that chapter, just one more thing, and then we'll go for the next chapter here. Let's go back to the whole thing. So I told you about the polarity, correct? What's unique about this shape here, the higher number, write it down. It's not inside the book even. Not inside, even zoom down, it's not inside. I think in the ebook, I did not write this chapter, but not then here you have it from me. The higher number of lone pair sets, the more polar the compound, the least the angle is. So the angle between in the central atom and its terminal will be less. So the more you add the lone pair, the more squeezed the angle will be, but the polarity will go up. Are you following me here? Let's look at this together. Let's look at this. Let's look at those lone pair now, and then we'll conclude for this chapter. So here, let's look at this. This one we have only one set of lone pair. The angle is 100, about 120, 118, close to 120. Correct? Everybody's following me here? So this one here, 118. Now, if you look at this one here, because this one I can't compare it because it has only one 3. This is 3 zone. I cannot compare it unless I have another 3 zone. But let's do this one here. Let's do this one here, guys. How many lone pairs here? This is 4 zones. You have to compare with the same number of zones. Here is 1 lone pair. Here's 4 zone. I have what? 2 sets. Which one will be polar? The one with 1 set lone pair or the 2? The 2. Correct? The 2. So here it is. The angle is 109. And the angle is less than 109. As a matter of fact, is 105 for H2O. So the higher number of lone pair, the number of the lone pair, the more they are there present, the more polar the compound, the less angle will be. So ammonia, look at the ammonia here. Ammonia, look at the ammonia here. Here. And look at the H2O. Those all of them four regions, correct? We said we don't care about the main thing is 4 regions. So here it is. Now, if you asked, and why? Which one is more polar? H2O or ammonia? That's 4. Why? In ammonia, we have 3 single bonds and 1 lone pair. In H2O, we have 2 single bonds and 2 lone pairs. The sum of both cases, 4 regions or 4 groups or 4 zones or 4 units, meaning the same thing. So, now, which one is more polar? H2O, why? It has 2 sets of lone pair, correct? It's more polar than ammonia, and that's really true. So we have our prediction is from the whisper helped us to determine more the polarity, which one is more polar. Now, the angle between nitrogen, here it is, nitrogen and the lone pair and the nitrogen here, 109, correct? And here, 105, correct? Can you see that? 105. So 2 lone pair sets have caused the angle to be what? Less. Are you following me here? So if I have a theoretical one, one, whatever, 2, so just a molecule here with 3 sets of 1, 2, 3, 4, 5, 6, something like this. This is X, not oxygen. Oxygen, say X, and it has 3. So X. So I have 3 sets of lone pair, and this is one single bond. This one will be more polar, correct? This one will be theoretical molecule, will be more polar, and the angle will be not 105, maybe 102 or something. The angle will be around maybe 102. Are you following me here? So the angle will be squeezed even further. Let's look at this now. Let's look at the number 5. Let's look at number 5. This is a little bit complex, but we can manage here. So without lone pair, you can see the angles is 90 and 120. Can you see the number? And if they are all the same, so this molecule will be nonpolar. If all the X's are the same atom, this is nonpolar. However, when you introduce this one here, has 1, this one has 2, this one has 3. Which is more polar from all of those? Which one is more polar? This one is more polar, correct? This one is more polar. With the angle is all of them here is 180, by the way. That's all of this 180. So you will see that the 90 degrees will be a little bit from the side will be different here. This angle's here, less than 90. See here, this is less than 90. And here even will be least a little bit than 90 by 89, 87, something like this. So this will conclude this chapter here. And I'll stop recording.